So this is going to be our introduction into section 1.3, which we will talk about in class on Monday. So we're going to talk about counting. And actually, in general, counting can be quite hard in mathematics. So what we're going to talk about in this video and in class as well is certain scenarios in which we can count the number of ways something can happen so that we can use those ideas for probability purposes. You'll also talk about doing different types of counting things in discrete mathematics if you haven't already. Might do some of it in a number theory class. There are other places where you all do some counting. But in general, counting is a difficult thing to do. So we're going to have a few ways to look at different scenarios and determine how to calculate, how to count the number of ways those scenarios can actually happen, because that is important when we're dealing with probability. So our first way that we can do counting is just a kind of a simple thought, but it's important thought nonetheless, and that's what's referred to as the multiplication principle. So what that says is that if you can perform task 1 in m ways and perform task 2 in n ways, then the way you find the number of ways to do task 1 followed by task 2 is simply just multiply m and n together. So let's look at an example here. So let's say a bicycle combination lock has 4 digits, and each digit can be an integer between 1 and 8 inclusive. So the inclusive part just means we're going to include the 1 and 8. So the first problem asks for how many combinations are possible. Well, we've got 4 digits, so there's 4 tasks to complete. I like to think of that as tasks, right? We have 4 different digits. Those are the tasks we need to do. And for each of these tasks, we're going to choose an integer between 1 and 8. So we have 8 ways to complete each of those tasks. So the possible number of combinations in this case, according to the multiplication principle, I've got tasks one after the other. Pick the first, then pick the second, then pick the third, then pick the fourth. There's 8 ways to do each of those, multiply together to get 4096. So let's change it up a little bit. Let's see how many combinations end in a multiple of 3. Well, we still have the 4 tasks to complete. There's still 4 digits to choose. Now, again, to end in a multiple of 3, we just want the last digit to be a multiple of 3. So it doesn't matter what the first digits are. So we still have 8 ways to choose each of the first 3 digits. But we want the last one to be a multiple of 3. Well, and that means it has to be a 3 or a 6. So there's 2 ways to choose the last digit. So that gives us a total number of possible combinations of 1024 when we multiply those again together. How about distinct digits, meaning we're not going to repeat the digits? So we still have 4 digits to choose. There's still 8 ways to choose the first digit. However, once we pick that first digit, we can't use it again, right? So that means that for the second digit, there's only 7 possibilities to choose, right? We had 8 for the first, but now we only have 7 for the second. Now, again, when we go to the third one, I can't use what I used for the first digit or the second digit. So there's 6 ways to choose the third digit. And likewise, there are 5 ways to choose the fourth digit. Now, again, we've done this in task, right? Chose the first, then chose the second, then chose the third, then chose the fourth. So again, according to the multiplication principle, we'll multiply those 4 together and get the number of possibilities being 1680. This last one's an example of what we refer to as a permutation. So from a permutation, we've got distinct objects, right? In this case, our distinct objects were the integers 1 through 8. So, or 8 of those, so n would be 8 in the previous example. We're going to select r of them. So in this case, we selected 4 of the digits. There were 4 digits to choose. And without replacement. So in that case, it means that without replacement means that you're not going to have any repeats, right? So as I said, distinct digits in the problem. So this is a without replacement problem. And also in this case, we're making a lock combination. Well, if I do a lock combination, the order in which the numbers appear matters. So the order of selection matters. So that's what defines a permutation. N distinct objects, selecting r of them at a time, but without repeats, and the order in which you select them matters. So like I just mentioned, we had a permutation in that previous example because order of selection mattered because we're making a combination for a lock. And we know that n was 8 because the 8 refers to the distinct objects or the distinct integers in this case, and the 4 was how many of those you were selecting. The notation, we're going to use this NPR notation. So we have a subscript n in the front and a subscript r in the back, P for permutation. Well, how do we get the formula? Well, just like we filled out these digits to begin with, there were n ways to choose the first digit. There were, once you fix that first digit, there's one less number of ways to fill in the second digit. Once we get the first two, there were two less ways to fill in the third digit. So we've got n times n minus 1 times n minus 2, all the way down to n minus r plus 1. Okay, so this is, you've already selected the first r minus 1, so you can't take any of those. Okay. And a little bit nicer formula, another nicer way to write this formula is you've got n factorial on top. Remember, n factorial means you start at n, decrease by 1, and multiply all together. So n times n minus 1 times n minus 2, and so on, over n minus r factorial, canceling off what would have been on the end here, because the next term would be n minus r if I kept going with n factorial. All right, so this is from your book. So let's go to this example. We've got a collection of 9 paintings. 4 are going to be selected to be hanging side by side in positions 1, 2, 3, and 4. How many ways can this be done? So we're going to hang them side by side. So the order matters. You've got 9 paintings. You can't hang the painting more than one time. So it's without replacement. And the order of selection matters because we're going to order them on the wall. We've numbered the positions, 1, 2, 3, 4. The order matters here. So that's a permutation. 9 paintings to choose from, 4 being chosen. So this is your N and your R. So that's why we've got 9P4. This is the formula, but in this, a problem like this, that's a smaller one, you might as well just think about it as 9 ways to choose the first, 8 ways to choose the second, 7 ways to choose the third, 6 ways to choose the fourth. Notice that your division here, you would have had a 5 factorial on bottom. Notice that's basically killing off the 5 factorial that would be on the end here if you wrote out 9 factorial. And we have 3024 in this case. All right, so this leads us to the concept of what we refer to as a combination. So notice that we had the order mattering here. So the difference between a permutation and a combination is that the order of selection does not matter. That's the difference between the two. Otherwise, they're identical in distinct objects. Selecting R of them without replacement is just whether or not the order matters. That's what refers to as a combination. So we're going to change this example up a little bit and show what it would look like for a combination. But first, let's get some notation and what the formula looks like. Just like we had NPR, we're going to use NCR for combination, or actually I will use this one on the right more often. This is what usually is referred to as a binomial coefficient. This is this is related to when you expand out a binomial to higher and higher powers. You see this in discrete, for example. So we'll use this notation for combinations a lot more than we'll use this one. This one you'll see on your calculator probably, but this is the one we'll use when we actually write out the notation. All right, so how do we get a formula for this? Well, we said that the only difference between combination and permutation is the fact that the order doesn't matter. Well, if the order did matter, NPR gives us the number of possibilities if you have selecting R objects from a collection of N of them without replacement, if the order mattered. But think about if I'm selecting R objects, so if the order doesn't matter, I can rearrange those R objects any way I want, and it's still the same selection. Think about it in terms of if you were getting dealt a hand of cards. If you get dealt a hand of cards, the first thing you do is pick them up and you move the cards around to however you want to see them in your hand, because the order doesn't matter to you, right? It's just what cards do you have in your hand, same idea. So we need to divide out of this all of the rearrangements that are possible. Well, if there's R objects, there's R factorial ways to rearrange a single selection. So for your formula for NCR, or number of combinations, or the N choose R is what I usually will say is N choose R, that this NPR over R factorial is your formula. And then if we plug in the formula for NPR, you get this. So we get N factorial over R factorial, N minus R factorial. All right. So let's go back to that previous example. Suppose they just want to loan 4 of the, instead of putting the paintings on the wall in certain positions, suppose they just want to loan the paintings to another museum. How many ways can we do this? Well, again, this is a combination because once they're just going to choose 4 paintings. They're not going to be the ones hanging them up. So it doesn't matter the order in which they choose 4. They're just going to choose 4 of them. So that's why that's a combination. So 9 choose 4. The formula then is 9 factorial over 4 factorial times 5 factorial. And you get 126 in this case. All right, let's do another example. Let's say you have 8 boys and 7 girls. The teacher is going to select 3 of the children without replacement. And it says calculate the probability that the number of boys exceeds the number of girls. Okay. So for probability, I need number of ways, number of total ways. I need the sample space, the size of the sample space. And I also need the size of the event. So this first calculation that I have here on the screen is the size of the sample space. There are 15 total children. And we're choosing 3 of them. All we're trying to calculate is if the number of boys exceeds the number of girls. So this is going to be done without replacement, but the order doesn't matter because we're just making a selection and counting number of boys, numbers of girls. So the order doesn't matter. So that's why we're using combination here. 15 choose 3 is 455. Okay. So let's think about how a selection, the number of boys, can exceed the number of girls. Well, for that to happen, there has to be 3 boys and no girls, or there have to be 2 boys and 1 girl. Notice that these are mutually exclusive ideas, right? I can't have 3 boys and 2 boys and a girl selected at the same time. So I've split this up into mutually exclusive cases. How many ways are there to calculate or to choose those selections for the first one to select 3 boys? Well, in the first case, there are 8 boys, and we're selecting 3 of them, again, combinations. So there's 56 ways to choose the boys. 3 boys, sorry. And then if no girls are selected, there's only 1 way to select no girls. All right, let's look at the second case. In the second case, let's think about doing this as tasks. First, choose the boys, then choose the girls. Choosing 2 boys from 8, 8 choose 2 is 28. Choosing 1 girl from 7, 7 choose 1 is 7. So 28 ways to select the 2 boys, 7 ways to select the 1 girl, and we've broken this into tasks. So the multiplication principle says we multiply those two ways and get 196 ways to select 2 boys and 1 girl. Okay, so back again, let's look at this. 56 ways to select 3 boys, 196 ways to do 2 boys and 1 girl. Okay. They were mutually exclusive. So we're basically finding the number of things in a union. So we would add those 2 pieces together. 56 plus 196 is 252. Total selections where the number of boys is above the number of girls. This was our event. So this is the number of elements in our event. This is what we wanted. Boys exceeding girls. This was our total size of our sample space. So then our probability that we want here is 252, the size of the event, over the 455, the size of the sample space. And if you want to reduce your fraction, that goes to 36 over 65. We're going to do more examples of these counting types of things, but I wanted to give you an introduction of how to do this and the kinds of problems that we'll see going forward trying to calculate probabilities by doing counting.